picture this scenario for a moment, all right? You're cruising down the highway in a high-performance hybrid vehicle.
Oh, nice.
Right. It's a beautiful day, weather is perfect, music is playing, and everything about the drive just feels incredibly smooth.
A perfect commute.
Exactly.
Yeah.
You have your foot on the accelerator, the car is just eating up the miles, and you are, frankly, entirely oblivious to the microscopic war being waged beneath your feet.
Right.
But then, deep within the power control system, this incredibly thin layer of thermal paste, we're talking no thicker than a human hair, right? It finally gives out. It fails.
Yeah, that's the nightmare.
And suddenly, without a single warning light on the dash, without a stutter of the engine, the vehicle completely loses all propulsion. You are just coasting, completely powerless. A heavy hunk of metal moving at 70 miles per hour, surrounded by traffic.
It is absolute nightmare fuel. I mean, when you work in automotive safety, that the sudden silent loss of high-speed propulsion is literally the scenario that keeps you up at night.
I can imagine.
And preventing that specific nightmare is exactly what we're dissecting today.
Right, because today we are tearing apart the engineering architecture that stops this from happening. We're going deep into a profoundly detailed set of engineering protocols, specifically the B10 cooling insufficiency and thermal resistance rise fault protocol.
It's quite a mouthful.
It really is a massive mouthful of engineering jargon, but it is one crucial piece of a master list of 45 core faults developed for hybrid dual motor power control systems, or PCS.
Yeah, PCS is the heart of it all.
And I want to be clear right off the bat, even if you have no background in automotive engineering, even if you don't know the difference between a wrench and a screwdriver, you need to hear this.
Absolutely.
Because what we're looking at is an absolute masterclass in how modern engineering manages extreme, violent, and entirely invisible forces just to keep you alive on your commute.
That's the key right there, the stakes. We aren't just talking about making a car run, a little more efficiently or just extending the battery range. We are analyzing a system that is engineered to meet what the industry calls ASIL D requirements.
And we should probably define that for everyone because that term comes up constantly in these specs.
Yeah, ASIL stands for Automotive Safety Integrity Level. It's a risk classification scheme. It runs from A to D, and D is the absolute highest, most stringent classification possible.
So no room for error.
Exactly. It represents situations where a system failure can literally mean life or death, usually involving the potential for severe injuries to multiple people.
Wow.
When a system is rated ASIL D, the engineering tolerances aren't measured in, like, good enoughs or we'll fix it in a software update. They are measured in fractions of a millimeter and in milliseconds of reaction time.
Because if the system fails, it has to fail safely, right?
Right. It must fail safely, autonomously, and this is the crazy part, faster than a human can even blink.
It is genuinely mind-blowing to realize how much invisible safety netting is beneath us. I mean, I always thought about car safety in terms of airbags and crumple zones, the things that save you during a crash.
Yeah, the physical hardware of a crash.
Exactly. But this entire architecture is about preventing the crash from happening in the first place by stopping the hardware from literally melting itself.
And melting is not an exaggeration here. The power control system is the brain and the brawn of a hybrid, or EV. It takes the direct current, the DC power from the massive battery pack, and rapidly switches it back and forth to create the alternating current, the AC power, that actually drives the electric motors.
And I'm guessing that switching process generates a ton of heat.
An immense amount of heat.
And heat is the real enemy here. When I first saw the term cooling insufficiency in the documentation, I'll admit my mind went straight to the obvious.
Like a broken radiator.
Yeah. I thought, okay, it's a broken fan, maybe a busted radiator, or a rat chewed through a coolant hose. But the reality is a much more insidious, microscopic battle.
Oh, entirely.
We are talking about fluid dynamics breaking down, mechanical stress tearing metal apart at the atomic level, and thermal fatigue. So I want to start by looking at what I've been calling the 4 horsemen of thermal failure.
I like that.
Yeah. And the first one is TIM degradation and something called the pump-out effect.
To really grasp the pump-out effect, we have to zoom way in on the physical sandwich of components inside the PCS.
Okay, let's zoom in.
At the very heart of the system, you have your power semiconductor chips. These are the components actually doing the heavy lifting, switching hundreds of volts and hundreds of amps, thousands of times a second.
So they are working incredibly hard.
Right. And because of the electrical resistance inherent in the silicon, they generate massive concentrated heat. These chips sit on a layer called the direct bonded copper, or DBC, substrate.
Which is what, exactly?
It's essentially a ceramic board sandwiched between two thick layers of copper. And below that substrate, you have your heavy aluminum heat sink, which is supposed to draw all that heat away.
Okay, so you've got this intensely hot copper plate, and you need to attach it to a cold aluminum plate. But I'm guessing you can't just slab a flat piece of copper onto a flat piece of aluminum and call it a day.
You really can because of the microscopic reality of manufactured surfaces. I mean, to the naked eye, a polished copper plate and a machined aluminum block look perfectly flat.
Sure.
But if you were to look at them under a powerful microscope, those metal surfaces look like rugged mountain ranges. They're full of microscopic peaks and valleys.
So if you just bolt them together, only the very tips of those microscopic mountains actually touch.
Precisely.
Ah.
The peaks touch, but you are left with millions of tiny interconnected valleys between the plates. And those valleys are filled with air.
And air is bad for cooling, right?
Oh, air is a terrible conductor of heat. In fact, it is a fantastic thermal insulator. Think about a puffy winter jacket or double-paned windows. They use trapped air to stop heat from moving.
Which is the exact opposite of what you want when you are trying to cool down a power module that might hit 150 degrees Celsius.
Exactly. So the engineers have to fill those microscopic valleys. And that's where the TIM comes in.
Yes, thermal interface material, or TIM.
Right. In these automotive applications, it is usually a highly engineered thermal silicone grease or a specialized phase change material that actually softens when it gets hot.
Okay, so it melts into the gaps.
Yeah, the entire job of the TIM is to ooze into all those microscopic valleys, displacing the air and creating a continuous, solid physical bridge for the heat energy to flow from the hot copper to the cooled aluminum.
Okay, so you've got this high-tech thermal grease keeping things cool. That makes sense. But the environment inside a vehicle isn't a climate-controlled laboratory.
No, it is brutal.
Right. These components are subjected to extreme temperature cycles. You could leave your car parked outside in a blizzard at -40 degrees Celsius, start it up, and within minutes push it hard onto a highway where the internal components rocket up to positive 150 degrees Celsius.
And that extreme, rapid temperature swing is exactly where the laws of physics turn against the hardware. Every material in the universe expands when it gets hot and shrinks when it gets cold.
Just basic physics.
Yep. It's dictated by something called the coefficient of thermal expansion, or CTE. The problem is that copper, aluminum, and the silicone thermal grease all have entirely different CTEs.
Oh, so they expand and contract at completely different rates?
Exactly.
So when the system heats up, the aluminum might expand significantly while the copper expands a little bit less.
You've got it. This mismatch creates severe thermal-mechanical stress. As the metal plates heat up and cool down, they don't just expand laterally. They warp and flex slightly. They bow inwards and outwards.
Like they're bending.
Yeah. Over thousands of heating and cooling cycles, these heavy metal plates are essentially acting like a giant microscopic bellows. They physically squeeze the thermal interface material.
Oh, wow. It's like a tube of toothpaste. If you imagine those heavy metal plates as your fingers holding a tube of toothpaste, and the extreme temperature changes are you constantly squeezing the tube and releasing it over and over and over again.
That is a perfect visualization.
Eventually, that toothpaste, or in this case, the thermal grease, is going to be physically pushed out of those microscopic gaps. It just gets squeezed out the sides.
Right. The constant warping literally pumps the grease out from between the plates, hence the pump-out effect. And to make matters worse, extreme sustained heat can cause the silicone oils inside the TIM to simply evaporate or dry out over time.
Leaving what? Just dust.
Basically, yeah. It leaves behind a brittle powder that eventually just crumbles away.
And when that paste is gone, whether it pumped out or dried out, those microscopic valleys come back. The air gets back in.
And the return of those air gaps is catastrophic. When the air replaces the TIM, you see an exponential, incredibly dangerous spike in thermal resistance. Heat transfer just plummets.
So the heat gets trapped.
It hits a wall of air and has nowhere to go, so the temperature inside the chip skyrockets.
Which perfectly sets up the second horseman of thermal failure, which is die-attach fatigue. And this one is also rooted in that same physics concept, things expanding at different rates. But now we are looking even deeper inside the module, right?
Yes, we are moving up from the heatsink and looking right at the power chips themselves, the semiconductor chips.
Okay.
These are usually silicon carbide MOSFETs or IGBTs.
Let's pause right there because I feel like we need to unpack that. What exactly is a silicon carbide MOSFET, and why is it generating so much heat in the first place?
Good question. A MOSFET, stands for metal oxide semiconductor field effect transistor. But honestly, you can just think of it as an incredibly fast, solid-state electrical valve.
A valve for electricity.
Right. Its job is to take the steady, flat electrical pressure from the battery and chop it up into waves that push the motor.
Mm-hmm.
But it isn't doing this a few times a minute. It is opening and closing thousands, sometimes tens of thousands of times a second. And the material it's made of, silicon carbide, is crucial here. Traditional silicon chips would just melt at the power levels required for modern EVs. Silicon carbide is a much more robust, wide bandgap material that can handle massive voltages and higher temperatures.
But even with silicon carbide, there is still resistance. I mean, it's not a perfect superconductor.
Right. Every time that valve opens and a massive surge of current rips through it, the electrical resistance of the material creates instantaneous, intense heat. This is a phenomenon known as power cycling.
So it's constantly heating up and cooling down.
Exactly. The chip heats up violently when you step on the gas and cools rapidly when you let off. Now, this silicon carbide chip has to be physically and electrically attached to that copper substrate we talked about earlier.
And they do that with a die-attach layer, which is essentially a specialized glue, right? Usually some kind of high-performance solder.
Correct. But here is the fatal flaw. The silicon carbide chip and the heavy copper plate beneath it have vastly different coefficients of thermal expansion.
The CTE mismatch again.
Yes. When that massive surge of power hits the chip gets hot instantly and tries to expand. The copper underneath is much larger, it acts as a heat sink, and it expands at a totally different rate.
So the two materials are basically physically fighting each other.
It is a microscopic tug of war happening thousands of times a minute. And the rope in that tug of war is the die-attach layer, the solder holding them together.
Oh, that sounds bad for the solder.
It is. Over time, this intense repetitive shearing force, the chip pulling one way, the copper pulling another, causes the solder to fatigue. It develops microscopic cracks at the edges.
And as those cracks grow, the chip begins to physically peel away from its foundation. It delaminates.
And this is where the physics become truly terrifying.
Yeah.
Because the relationship between that lost physical connection and the resulting heat is not linear.
Wait, what do you mean by not linear? If I lose 10% of the solder connection, doesn't the cooling efficiency just drop by 10%?
You would think so, but no. Think of the solder joint like a highway carrying both electricity and heat. If you close a lane on the highway, the cars don't just disappear, right? They all cram into the remaining open lanes, causing a massive traffic jam.
Right, everyone gets bottlenecked.
Exactly. When the edges of the die-attach layer crack, all the electrical current and all the heat energy are forced to travel through the remaining intact center of the solder joint. This creates extreme localized crowding of the current.
Ah, so the remaining healthy part of the connection is now doing twice the work, which means it generates exponentially more heat.
Exactly. This creates what engineers call a fatal hotspot. Because this one tiny area is now drastically hotter than the rest of the chip, it expands even faster, which violently accelerates the tearing and cracking of the remaining solder.
It becomes a runaway feedback loop.
A total runaway loop. The crack causes a hotspot, the hotspot causes more cracking, until the chip literally tears itself off the cooling plate and vaporizes itself in a complete thermal meltdown.
Okay, that is completely terrifying. So we've got the thermal paste getting squeezed out like toothpaste, and we've got the chips literally ripping themselves off their foundations due to microscopic heat warping. What's the third horseman?
The third is coolant channel scale and blockage. This one operates on a slightly larger scale, dealing with the liquid cooling system that flows through the aluminum heatsink.
Now, this feels a bit more traditional. This is like the radiator issues people are used to in combustion engine cars, right? A broken water pump, a leak, a blocked pipe.
It is more traditional, yeah, but it is incredibly lethal to an ASIL D system. The entire heat transfer system relies on forced convection pushing cold liquid past hot metal to carry the thermal energy away.
Right.
If you lose that fluid flow because a pump seizes up, the convective cooling drops to zero almost instantly. The heat has nowhere to go.
But looking at the engineering protocols, it isn't just about a physical blockage, like a piece of debris getting stuck in a pipe. The really insidious problem they highlight is chemical scaling on the aluminum walls.
Right. It's a chemical degradation process. Over time, the chemical composition of the liquid coolant interacts with the hot aluminum walls under high pressure.
Even with the special EV coolants.
Even with specialized automotive coolants, the extreme heat can cause minerals and chemical compounds to physically precipitate out of the liquid. They separate from the fluid and bake onto the inside walls of the cooling channels.
It sounds exactly like the hard water scale that builds up on the inside of an electric kettle. If you use it for a few years, you get that crusty white layer on the heating element.
That is the exact mechanism. Now think about what that crusty layer actually is. It's a non-metallic mineral deposit, which means it is a fantastic thermal insulator.
Oh, no!
Yeah, so over tens of thousands of miles of driving, this scale builds up and acts like an insulating blanket lining the inside of the aluminum pipes.
So the car's computer might think everything is fine, the pump is running at 100%, the fluid is flowing perfectly, there are no leaks. But the system is still overheating because the heat literally cannot cross that crusty barrier to get into the liquid.
Exactly. The thermal resistance of the entire liquid cooling loop increases drastically, but totally invisibly. The heat backs up into the aluminum, which backs up into the copper, which backs up into the silicon chip, and you get a failure.
Okay, let's unpack the final root cause, the fourth horseman, preload loss and joule heating.
This is a fun one.
Now, I have to admit, when I was reading through this section, I got genuinely stuck. I stared at this part for a good 20 minutes because my brain was trying to map it to something I actually understand.
It's a bit abstract.
It really is. The protocol explains that DC capacitor terminals and the high-voltage bus bars, which are the thick metal bars carrying the massive power loads from the battery to the inverter, are bolted together.
Right.
And it says that assembly defects can cause the axial preload, which is essentially just the tightness of the bolt, to be insufficient. And then road vibration makes it looser, increasing contact resistance.
That is correct.
But here's where I have to push back, because I feel like I'm missing the underlying physics. The bus bar is just a big power cable on the outside of the main chip assembly. It's external to the sensitive microscopic silicon we've been talking about.
It is external, yes.
If a bolt holding that heavy metal bar is a little loose, I get that it might spark or you might lose some efficiency, but how on earth does a slightly loose bolt on an external bus bar end up causing an entire power module buried inside the casing to melt down?
It is a fantastic question, and to understand it, we have to look at the atomic reality of electricity and a principle called joule heating.
Okay, joule heating.
When we talk about electricity flowing through a wire, we often use the analogy of water flowing through a pipe. But electricity is actually electrons moving from atom to atom through a conductive material like copper.
Okay, electrons moving through the atomic structure.
Now, in a high-performance hybrid system, these bus bars aren't carrying a trickle of electricity like a household lamp. They're carrying a massive amounts of current, hundreds of amps.
So it's a huge flow.
An unfathomable number of electrons rushing through that metal every millisecond. Now, joule heating dictates that when electrical current flows through any material that has resistance, it generates heat.
Because the electrons are physically colliding with the atoms of the copper as they move, right? It's essentially atomic friction.
Exactly. Atomic friction. The math for joule heating states that the heat generated is equal to the electrical current squared, multiplied by the resistance.
Current squared. Got it.
Now imagine that bolted connection on the bus bar. If the factory worker didn't torque the bolt perfectly, or if years of driving over potholes rattles it slightly loose, the two flat metal surfaces of the bus bars are no longer pressing tightly together. Microscopic gaps open up.
So the surface area where the electricity can cross from one bar to the other is drastically reduced.
Right. You have all these electrons rushing down a wide multi-lane highway, and suddenly, because the surfaces aren't touching perfectly, all the lanes are closed, except for one tiny dirt road. All the current has to cram through that microscopic point of contact. The electrical resistance at that specific joint skyrockets.
So it's like a massive traffic jam, but instead of cars just slowing down, the cars are scraping against the guardrails, crashing into each other, and instantly catching fire because of the friction.
Because of the math current, squared times resistance, even a tiny increase in resistance at a joint carrying hundreds of amps results in a violent exponential spike in heat. That one loose bolt can generate temperatures rivaling a blowtorch.
Okay, but it's still outside the chip module. How does it destroy the chip?
Because copper is one of the best conductors of heat on the periodic table. That violent temperature spike at the bolted joint doesn't just dissipate into the air. It travels straight down the solid copper bus bar.
Oh, wow.
The bus bar acts as a thermal highway, conducting that massive heat load directly into the bottom of the power module it's connected to.
So it's pushing the heat inside.
It is essentially injecting high-intensity heat from the outside world directly into the sensitive semiconductor chips, bypassing all the internal cooling systems and causing localized thermal runaway.
Wow. Okay, so to recap our four invisible enemies, the thermal paste gets pumped out by the metal warping like a bellows.
Yep.
The silicon chips literally crack off their base due to thermal stress and a microscopic tug of war.
Right.
The cooling pipes get insulated by a crusty chemical buildup, and a single slightly loose bolt turns the power cable into a literal blowtorch.
Just sounds bleak when you put it like that.
It is a miracle these vehicles can drive down the street at all. Which brings us to how the car actually survives this. The software and hardware co-diagnostics, the ASIL D defense system.
This is where the engineering gets really cool.
Because obviously the car has to know this heat is building up before the system physically melts. And the architecture they used to detect this, frankly, blew my mind.
It is a phenomenal, multi-layered piece of engineering. To meet those stringent ASIL D safety standards, you cannot rely on just one sensor or one line of code.
Right, what if that sensor breaks?
Exactly. If that one sensor fails, people could die. You need a deeply redundant, multi-tiered architecture that combines raw, physical hardware interrupts with incredibly sophisticated software prediction models.
Let's start with the base layer, the first line of defense. Hardware out of range checking.
Okay.
The protocol states that NTC thermistors are placed right on the DBC board, right next to the chips. These convert the physical temperature into an analog voltage, which gets sent directly to the main microcontroller, the MCU, something like the AURX TC3XX chip.
Yes. NTC stands for negative temperature coefficient. It is a tiny physical thermometer, a specialized resistor, placed as close to the chaotic heat of the power chips as physically possible.
Okay, so a tiny thermometer.
Right, but it has a very specific property. As its physical temperature goes up, its electrical resistance goes down. By running a tiny constant current through it, the MCU can measure the changing voltage to determine the exact temperature.
Okay, so it's a standard temperature sensor. But the hardware architecture around it is fascinating. The hardware comparator forces a strict safe zone between 0.5 volts and 4.5 volts.
Yes, very strict.
Why that specific, seemingly arbitrary range? Why not just use the full spectrum, 0 to 5 volts, to get more resolution?
That artificial restriction is actually the genius of the safety design. By restricting the normal operating range to between 0.5 and 4.5 volts, the physical hardware can instantly detect catastrophic sensor failures without needing any software to think about it.
Oh, I see. If a rock kicks up and severs the wire to the sensor, the voltage drops completely to 0.
Exactly. Because the acceptable range starts at 0.5 volts. If the hardware sees exactly 0.0 volts, it knows instantly in microseconds that it isn't reading a really cold temperature. It knows the wire is broken.
That's brilliant.
And conversely, if the insulation on the wires melts and it shorts out to the 5-volt power rail, the hardware sees a full 5.0 volts. It knows immediately that it's a short circuit.
So it doesn't even need the software code.
No. If the signal steps outside that 0.5 to 4.5 volt boundary for even a fraction of a millisecond, the physical hardware comparator trips an alarm and shuts the system down. It is a hardwired reflex.
That is incredibly clever. But here's where things get really deep and where I actually thought I found a massive flaw in the engineering logic.
Oh, let's hear it.
I was reading the documentation, and it explicitly notes that these physical NTC sensors have a thermal conduction lag of 50 to 200 milliseconds.
Yes, the thermal time constant.
Right. Meaning, from the exact millisecond the silicon chip actually gets dangerously hot, to the moment that heat physically travels through the copper substrate, warms up the casing of the NTC sensor, and registers a voltage change in the computer. Up to a fifth of a second has passed.
Yep, 200 milliseconds.
Now, you said earlier that a silicon carbide chip can undergo thermal runaways incredibly fast. In the world of high-voltage shorts, isn't 200 milliseconds an absolute eternity? Why rely on a slow thermometer at all if the chip is going to be vaporized before the thermometer even registers a change?
You've hit on one of the most fundamental challenges in power electronics. In an ASIL D system, 200 milliseconds is indeed an eternity. It is far too slow.
So I was right.
You were. If a short circuit occurs, the chip will be completely destroyed before the physical heat wave ever reaches the sensor. The engineers know the physical sensor is too slow to save the car in a dynamic event.
So what do?
And that is exactly why they don't rely purely on physical reality. They use the software to run a digital twin. Specifically, the system runs a real-time dynamic Foster-RC thermal network model.
Okay, this is where it starts sounding like science fiction. A digital twin. So the computer is simulating the heat of the chip in a virtual space.
That is exactly what it's doing. Instead of waiting for the physical heat to slowly crawl across the copper board to the thermometer, the software calculates what the temperature of the chip must be right at this exact microsecond, based entirely on the physics of the electricity flowing into it.
How does it do that? How do you calculate heat without measuring heat?
By measuring the work being done. The Foster RC network uses real-time telemetry from the electrical system. It looks at the exact phase current flowing through the motor, it looks at the DC voltage coming from the battery pack, and it looks at the high-frequency switching speed of the transistors.
So it knows exactly how much electricity is entering the chip.
Right, and because the engineers know the exact physical properties of the silicon carbide, they know exactly how much of that electricity is naturally lost as heat due to resistance.
Oh, I see.
It's called power loss calculation. The software takes those three variables, current, voltage, switching frequency, and mathematically predicts the exact junction temperature of the inside of the chip instantly.
Foster RC. What does the RC stand for?
The RC in Foster RC stands for resistor capacitor. It uses a mathematical model where electrical resistance simulates thermal resistance and electrical capacitance simulates thermal mass. It entirely bypasses the physical thermal lag of the NTC sensor.
So the software is essentially saying, I just dumped a massive surge of electrons into this chip to accelerate the car. I know the math dictates that 5% of that energy turns into heat, so I know exactly how hot the center of the chip is right this second, even if my physical thermometer is still reading cold because the heat hasn't reached it yet.
Precisely. It outpaces physical reality with mathematics. It marries the slow, steady physical reality of the NTC thermistor, which is used to calibrate the baseline and account for the ambient weather outside, with the lightning-fast predictive mathematics of the Foster RC model to catch the instantaneous spikes.
That is brilliant, which leads right into the next layer of the software defense, which is the online thermal impedance observer.
Another great piece of code.
When I read this, it sounded like an algorithm designed specifically to catch those first three root causes we talked about. The slow degradation, the thermal paste getting pumped out, the die attach cracking, and the coolant scaling.
It is entirely dedicated to catching long-term degradation. The observer algorithm is incredibly clever because it doesn't just look for high temperatures.
Right, because high temperatures aren't always a problem.
Exactly. High temperatures can be normal if you are towing a heavy trailer up a mountain. Instead, it looks for changes in how the system heats up.
The documentation says the software waits for a moment when the car is under a heavy, steady load.
Right, like accelerating up a long, sustained hill. It waits for the electrical current to stabilize. During this steady state, the algorithm calculates the actual thermal resistance of the entire system in real time.
How does it do that?
It takes the mathematical heat generation from the Foster RC model we just talked about and compares it to the temperature of the liquid coolant flowing into the heatsink.
So it knows how much heat is being created, and it knows how cold the water is?
Yes, and it checks that calculation against a pristine factory baseline programmed into the ECU. The fault protocol dictates that if this newly estimated thermal resistance climbs 20% above the factory baseline, it triggers a warning.
And it also mentions looking at the heating slope, or the time constant called tau. What does that mean?
Tau is a measure of thermal inertia. It's how fast a material heats up. You put a heavy cast iron pan on the stove, it heats up slowly, it has a large tau. If you put a thin aluminum foil pan on the stove, it heats up instantly, a very small tau.
Okay, that makes sense.
The software knows exactly how long the power module should take to reach a certain temperature. If the heating slope suddenly gets much steeper, meaning the chip is heating up much faster than it should for a given amount of power, the algorithm knows the thermal inertia has changed.
Because the physical connection has broken down?
Exactly. The software realizes, wait, I am generating 500 watts of heat, but the chip is getting hotter faster than it did when the car was brand new.
Wow.
The algorithm mathematically deduces that the thermal resistance has increased. It knows without ever physically seeing it that either the thermal paste is pumped out, a microcrack is formed in the solder, or the coolant pipes are lined with scale.
And the incredible part is the predictive power. This algorithm can spot the thermal paste aging out hours, days, or even weeks before a catastrophic failure actually occurs.
It's totally proactive.
It flags the B10 error code in the computer, illuminating the check engine light, warning the driver to service the vehicle long before the chips are in any real danger of crossing the point of no return.
That's the beauty of it.
Okay, so that is the prediction side. But what does the system actually do when the math says a critical failure is happening right now in the middle of a drive?
When things hit the fan.
Let's say a coolant hose completely blows off and the temperature is rocketing toward the red line. The documentation details an adaptive fallback and ASC strategy.
Right. Detecting the fault is completely useless if the system can't react autonomously to save itself and the driver. The strategy is broken into escalating levels of severity.
Level 1.
Level 1 is thermal derating. This kicks in if the chip's internal junction temperature hits 125 degrees Celsius, or if that predictive observer we just discussed throws a warning.
The spec sheet says it smoothly cuts motor torque at a rate of 500 newton meters per second down to just 30% of its maximum capability.
Yes, and the word smoothly is critical there. The goal is to reduce the heat generation without jarring the driver or causing a sudden loss of control.
You don't want the car to just violently jerk on the highway.
No, definitely not. By aggressively but smoothly cutting the torque demand from the driver's foot pedal, it drastically drops the electrical current flowing through the chips. Less current means less joule heating.
And that's often enough to save it.
Very often, just dropping the power to 30% is enough to let the struggling cooling system catch up, stabilize the temperatures, and allow you to link the car to a mechanic safely.
But what if limp mode isn't enough? Going back to my scenario, a rock strikes the radiator, the coolant completely drains out onto the highway in seconds. The temperature is going to skyrocket regardless of how much you degrade the torque.
That triggers level 2, the fatal fault.
Sounds ominous.
It is. If the software's digital twin calculates that the junction temperature has hit 175 degrees Celsius, the system knows physical meltdown is imminent. It must force the massive electrical inverter into a safe state instantly.
How fast?
The specification for this is an FTTI, a fault-tolerant time interval of less than 60 milliseconds.
60 milliseconds. That is literally faster than the blink of a human eye. The car has to realize it's dying, cut the power, and safe the electronics before you even know something went wrong.
It has to. And the exact response depends on how fast the physical vehicle is moving down the road.
Why does speed matter?
Because if you are traveling at high speeds, say over 80 kilometers per hour, the electric motors are spinning incredibly fast, acting as massive generators. If you just open the circuits and disconnect them, the high-voltage energy trapped in the spinning motor has nowhere to go and will blast back into the inverter, destroying it.
Oh, that makes sense. So what does it do?
So this system executes what's called a stepwise active short circuit, or ASC.
Active short circuit. Wait, you want to intentionally cause a short circuit? I thought shorts were bad.
An uncontrolled short circuit is catastrophic. A controlled active short circuit is a lifesaver. By intentionally shorting the motor coils together through the inverter chips, you clamp the DC voltage down to a safe level. The spec says under 720 volts.
And that protects the battery.
Yes, and you force the trapped magnetic energy in the motor to circulate harmlessly as current, rather than spiking as destructive voltage.
But wait, if you create a massive short circuit, doesn't that generate a mind-boggling amount of heat inside the chips doing the shorting?
Yes, it does. Which brings us to what I consider one of the most brilliant pieces of software engineering in this entire document, the alternating upper and lower arm ASC strategy.
Tell me about this.
When you force a high-speed motor into an active short circuit, massive current gets trapped circulating. If you just use the top half of the inverter circuit, the upper arm chips, to hold that short, those specific chips would absorb all that heat, exceed their thermal limits, and melt in a matter of seconds.
So what do?
The software rapidly alternates the short circuit between different physical chips. It commands the upper arm chips to close and hold the short circuit. They take the massive heat load for a few milliseconds, absorbing the punishment.
Okay, so they're heating up fast.
Right. Then right before they melt, the software opens them and instantly commands the lower arm chips to close and take over the short circuit, shifting the entire burden.
It is literally juggling hot potatoes. The software is passing this massive destructive ball of thermal energy back and forth between the top and bottom circuits so incredibly fast that no single physical component has to bear the total brunt of the extreme heat long enough to reach its melting point. It's buying time.
That's a fantastic analogy.
Yeah.
It is rapidly juggling the thermal energy to keep the hardware alive just a few seconds longer, allowing the vehicle to safely decelerate and the spinning motor to bleed off its kinetic energy.
And what if you're going slow?
Now, if you are moving at low speeds, under 20 kilometers per hour, the motor isn't spinning fast enough to generate a dangerous back voltage. In that case, the system doesn't need to juggle. It just uses active open circuit. It simply opens all the valves, disconnects the motor entirely, and lets the car coast to a stop.
It's just staggering. The car detects the heat using a virtual mathematical model, realizes it's going to die, and juggles an electrical hot potato in milliseconds to survive.
It is pretty wild.
But obviously, detecting a fault and desperately trying to survive it is the worst-case scenario. Avoiding the fault in the first place is the ultimate goal.
Always.
So let's pivot from the software running dynamically in the car to the engineers, the scientists, and the robots designing and building the hardware on the factory floor. This brings us to the DFMEA and PFMEA protocols, the engineering and manufacturing defenses.
DFMEA stands for Design Failure Mode and Effects Analysis. This is the stage where engineers look at a blank blueprint, analyze every possible way it could fail, and ask, how can we design the physical geometry of this object so it is structurally impossible for that failure to occur?
The protocol highlights a massive shift in how they design the cooling hardware itself. It mandates 3D dynamic thermal flow co-design.
Right.
Which implies that in the past, they used to design the electrical circuits first and then hand it to a different department to figure out how to bolt a water cooler onto it.
Exactly. The old way was sequential. The new way is fully integrated. They are designing the complex fluid dynamics of the liquid coolant alongside the electrical pathways from day one in a simulated 3D environment.
That makes a lot more sense.
And the source dictates that the aluminum heat sinks can no longer be flat plates. They must use specific, highly engineered geometries, specifically pin-fin or microchannel structures.
Pin-fin, meaning instead of a flat surface, the aluminum is machined into hundreds of tiny little spikes or pins sticking out into the water.
Right. Think of a bed of nails. By machining the aluminum into a forest of microscopic pins or incredibly narrow channels, you drastically exponentially increase the surface area of the metal that is touching the liquid.
More surface area means more cooling.
The coolant physically flows between and around these tiny pins, creating turbulent flow, which pulls heat away much faster than smooth, flat flow. The standard dictates this geometry must push the thermal resistance below 0.1 Kelvin per watt. It is a staggeringly efficient way to extract heat from the chips.
But I think the most fascinating part of the design phase is how they solve the die-attach fatigue we spent so much time on earlier.
Oh, the silver sintering?
Right. The issue where the chips literally rip themselves off the substrate because of the CTE mismatch and the microscopic tug-of-war. The protocol highlights a fundamental shift away from using traditional solder, moving to a material science breakthrough called nano-silver sintering.
This is a huge, critical leap in semiconductor manufacturing. Traditional solder is a metal alloy, usually containing tin, silver, and copper. It is specifically designed to melt at a relatively low temperature, around 220 degrees Celsius.
So it's easy to work with in the factory.
You heat it up, it turns to liquid, it wets the surfaces, and it cools into a solid joint. But because it melts easily, it is fundamentally soft. It degrades, creeps, and cracks under the extreme 150 degrees Celsius heat cycles we discussed.
Right. It can't survive the tug-of-war.
It simply cannot survive the tug-of-war for the lifespan of a vehicle.
So they threw out solder entirely. What is nano-silver sintering?
Sintering is a fundamentally different physical process than soldering. Instead of melting a soft alloy, they use a case made of pure nanoscale silver particles.
Nanoscale meaning incredibly microscopically small.
Yes, particles measured in nanometers.
Yeah.
Because they are so incredibly small, their surface energy is through the roof. During manufacturing, they place the chip on this silver paste, apply a massive amount of physical pressure, and apply heat. But crucially, it is not enough heat to melt the silver.
Wait, if it doesn't melt, how does it stick together?
Because of the high surface energy of the nanoparticles. When you apply heat and pressure, the atoms on the surface of these tiny particles become excited and actually diffuse into each other.
Wow.
They interlock and bond at the atomic level in a solid state. They fuse together without ever becoming a liquid.
And the specs on the resulting bond are wild. The text states that once the sintering is complete, the melting point of that new solid silver layer is 960 degrees Celsius.
Exactly. You use low heat to form it, but once the nanoparticles fuse into bulk silver, it takes nearly 1,000 degrees to melt it. And its thermal conductivity is roughly 200 watts per meter Kelvin, which is 3 to 5 times higher than standard solder.
So by switching to silver sintering, they practically eliminate the thermal fatigue. That silver layer is incredibly strong, massively conductive to pull heat away, and utterly unfazed by the 150-degree operating temperatures of the car.
It really is a game changer.
It provides an almost indestructible buffer against the micro-cracking and delamination that plagued older inverter designs.
Yeah, they solved the problem at the atomic level.
I also noticed something else in the design spec regarding the smaller components. The intense or bill of materials requirements. The spec mandates the use of Class 1 C0G ceramic capacitors and ultra-precise thin film resistors.
Yes, the component specs are rigid.
They aren't just opening a catalog and buying standard off-the-shelf electronics.
No, they cannot. This goes back to the ASIL D rating and the digital twin we talked about. Remember how the system measures temperature using the NTC thermistor by looking at microscopic changes in voltage?
Yes, the 0.5 to 4.5 volt range.
Well, the MCU needs tiny resistors and capacitors on the circuit board to filter and process that delicate analog voltage signal before the computer can read it. Standard resistors and capacitors change their electrical properties when they get hot. It's called temperature drift.
Oh, I see the problem. If your main temperature sensor is sending a perfectly accurate voltage down the wire, but the tiny resistor interpreting that signal on the circuit board changes its resistance just because it got hot from the ambient air,
Then the computer's going to calculate the wrong temperature.
the entire safety calculation becomes garbage. It might think the chip is safe when it's actually melting.
Exactly. Class 1 C0G is a specific dielectric material standard for ceramic capacitors. C0G essentially means it has a temperature coefficient of 0.
So it doesn't drift.
High-end thin film resistors and C0G capacitors are engineered with exotic materials to have virtually zero temperature drift. They perform with exact mathematical precision whether they are frozen at -40 degrees or baking at 150 degrees.
So the engineers have designed an absolute masterpiece on paper, but a blueprint is only as good as the factory actually building it. Which brings us to PFMEA, process failure mode and effects analysis.
The assembly line.
These are the ruthless process controls implemented on the physical assembly line. Because when you are building an ASIL D system, human error is simply not an option.
It really isn't. The margin for error is essentially 0. Remember the air gaps and the microscopic voids we discussed earlier? How air acts as an insulator.
Oh, the microscopic valleys, yes.
To prevent any voids from forming during that advanced silver sintering process, the factory utilizes 100% inline SAM testing on every single unit.
SAM stands for Scanning Acoustic Microscope. I had to look this up because it sounds so futuristic. How does sound let you see air bubbles inside solid metal?
It uses high-frequency ultrasonic waves, similar to medical ultrasound but at much higher frequencies, sometimes the gigahertz range. The machine fires a pulse of sound down into the power module.
Okay, sound waves through metal.
Sound waves travel at different speeds through different materials. It travels very well through solid copper and solid silver. But if that sound wave hits a microscopic pocket of trapped air, a void, the density change causes the sound wave to echo back aggressively.
Oh, I see.
The microscope measures those echoes to build a highly precise 3D topographical map of the inside of the solid metal joint.
And the tolerances they enforce based on that map are brutal. The protocol states that the voiding rates in the silver sintering must be less than or equal to 5% total across the entire massive surface area of the chip, with absolutely no single void larger than 1%.
Right.
If the machine fires its sound waves and detects a 1.1% air bubble,
The assembly line instantly locks down. That specific part is physically quarantined and scrapped. They do not allow a single microscopic bubble out the door because the physics models prove that 1.1% bubble will eventually become a thermal hotspot.
which will cause a catastrophic thermal runaway years down the road.
Precisely.
And they take the exact same ruthless approach to applying the thermal paste, the TIM. The protocol explicitly states, no human hands allowed. The application must be fully automated.
Because a human with a syringe is incredibly inconsistent. The paste is applied by fully automated stencil printing machines, followed immediately by 3D laser topography scanning.
Lasers now.
Yeah, a laser sweeps across the wet paste, measuring its height at thousands of points. The specification guarantees a perfect 50 micrometers of thickness, plus or minus just 10 micrometers, with absolutely zero air bubbles trapped inside.
10 micrometers. They're controlling the thickness of a viscous liquid paste to roughly the width of a human red blood cell.
They have to. Any thicker, and the thermal resistance increases. Any thinner, and it pumps out faster. They also implement 100% automated dual-stage helium leak testing on the aluminum coolant channels.
Why helium? Why not just pump it full of air and see if it holds pressure, like checking a bicycle tire?
Because air molecules are relatively large, and if you test with water, the water could cause corrosion. Helium atoms are incredibly tiny, and helium is an inert noble gas, meaning it won't react with the aluminum.
So they use helium gas.
They pressurize the internal cooling channels with helium gas at 4 bar pressure inside a vacuum chamber. If there's even a microscopic atomic scale fracture in the aluminum casting, where liquid coolant could eventually sweat out over 10 years and short out the high voltage barriers.
The helium will find it.
The tiny helium atoms will escape through that fracture. The sensors in the vacuum chamber sniff out the helium, and the part is instantly scrapped.
I want to return to the loose bolt problem from earlier, the bus bars that caused that violent Joule heating traffic jam. We talked about how human error, a worker under torquing a wrench, could lead to a meltdown. So how does this futuristic factory prevent that? You can't just eliminate bolts.
No, you can't eliminate the bolts, but you can remove the human element of torque entirely. The factory utilizes specialized torque angle servo screwdrivers. These are not your standard pneumatic impact wrenches. Before the bolt is even picked up, an optical character recognition or OCR camera system scans the bolt.
Wait, it's taking a picture of the bolt. Why?
To verify the chemical coating, the camera ensures the bolt has the exact required phosphate coating. The coating determines the coefficient of friction of the metal. If the friction is wrong, the torque reading will be wrong.
It is verifying the chemistry of the metal before it even turns the screw.
Yes. And then, as the robotic servo screwdriver begins to tighten the bolt, it doesn't just push until it hits a certain resistance. It monitors the friction curve and the torque angle in real time, reading the data hundreds of times a second.
Wow.
It measures exactly how many degrees the bolt has turned versus how much rotational force is required. The software knows exactly how the metallic threads should yield and stretch elastically as they tighten.
So if a bit of grit is in the threads, or if the metal is too soft, the curve looks wrong.
Exactly. If it senses poor clamping force, or if the friction curve deviates even slightly from the mathematical ideal, the assembly line stops instantly.
It's just so thorough.
This robotic verification guarantees that every single high-voltage connection has a physical contact resistance under 5 microohms. They are verifying the invisible electrical resistance by incredibly precisely measuring the physical twist of a bolt.
It is truly, genuinely mind-blowing. The engineers designed it perfectly on a computer, and the robots built it flawlessly on the line. But before this inverter ever gets installed into a consumer's vehicle, it must face the absolute tribunal of validation testing.
The final hurdle.
Which brings us to the final piece of the puzzle, DVP&R.
Design Verification Plan and Report. This is the stage where the manufacturer takes everything they've meticulously designed and built, and they try their absolute hardest to completely destroy it.
Just to prove mathematically that it can survive the real world.
Exactly.
The ultimate torture test. Let's look at the first test outlined in the protocol, the Power Cycling Extreme Endurance Test. Based on international IEC and AQG standards, they put the module on a test bench and blast the chip with massive phase currents, intentionally forcing the internal temperature to fluctuate by greater than or equal to 80 Kelvin in seconds.
They're artificially inducing that brutal thermal-mechanical stress, the CTE mismatch tug-of-war we talked about, on an accelerated timeline.
They want to break it.
They want to force the silver sintering to fail. And they don't just do this a few times. They pulse that massive heat 100,000 to 200,000 times continuously.
And the acceptance criteria are strict. After surviving 200,000 extreme temperature swings, the overall thermal resistance degradation of the system must be less than or equal to 10%. The voltage drop shift across the chips must be less than 5%.
And they verify it.
Right. They don't just take the computer's word for it. They pull it off the bench and run it back through the acoustic microscope to prove there is exactly 0% delamination in the silver layer.
If it miraculously survives that, it moves to the high-pressure vibration chamber. They strap the inverter module to a massive shaker table, simulating extreme, violent random vibration at 35 meters per second squared. This simulates years of driving over cobblestones and potholes.
But they do it while freezing and baking it.
Yes, while it's violently shaking, the environmental chamber puts it through rapid temperature cycling from negative 40 degrees to positive 125 degrees Celsius.
That's insane.
And if that wasn't enough torture, they simultaneously hook up the liquid cooling loop and pulse the channels with heavy 4-bar pressure blasts of coolant 10,000 times.
What exactly is this proving? I mean, this is beyond normal driving.
It proves the physical architecture can withstand reality. It verifies that those tiny aluminum pin fins inside the cooler don't develop fatigue cracks and snap off under intense vibration. It proves the thermal paste doesn't wash out or pump out when the metal is shaking and warping.
And the sensors?
It ensures the delicate NTC temperature sensor's accuracy doesn't drift more than 1 degree Celsius, despite being violently shaken and frozen. And crucially, it guarantees the electrical insulation resistance remains rock solid above 100 megaohms, meaning the high-voltage electricity won't break through the insulators and short out to the chassis of the car, which could electrocute a passenger.
And finally, the ultimate Kobayashi Maru test, hardware in the loop, or HIL, fault injection. I love this part of the document. Using an FPGA simulator or a massive physical dynamometer, they spin the electric motor to a screaming 12,000 RPM at full electrical load.
Pushing it to the absolute limit.
It is running at maximum capacity, pulling hundreds of amps, and then, while the system is at its absolute limit, the engineers literally pull the plug.
They intentionally inject a fatal fault.
They simulate an instant coolant blockage, dropping the liquid flow to zero instantly, or they simulate a massive 50% spike in TIM thermal resistance.
It is the moment of truth for the entire ASIL D software and hardware architecture. The physical destruction of the inverter is imminent and unavoidable if the system doesn't react.
And the pass-fail criteria are just as intense as the test itself. The digital twin software must detect the fault instantly, bypassing the physical sensor lag. It must drop the system into that stepwise active short-circuit safe state we discussed in under 60 milliseconds.
That 60 millisecond window is rigid.
It must clamp the surging voltage to less than or equal to 720 volts to protect the battery. It has to keep the demagnetization current under 550 amps so the motor magnets aren't destroyed.
And it has to survive the juggling.
Exactly. After all of that violent juggling of hot potatoes between the upper and lower chips, there must be absolutely zero secondary burnouts on the control board. The system has to save itself, completely autonomously, in less time than it takes a human being to blink.
When you step back and look at the totality of it, the material science of nanosilver sintering, the fluid dynamics of microchannels, the predictive lightning-fast mathematics of the Foster RC model, and the microsecond reflexes of the safety fallback.
Yeah.
You realize that modern electric and hybrid vehicles are less like traditional cars and much more like low-flying spacecraft.
Okay, let's take a breath and recap this incredible journey. We started with the terrifying realization that a microscopic air bubble in a layer of thermal paste could leave you completely stranded on a highway.
Which is wild.
We unpacked the 4 horsemen of thermal failure: the TIM paste getting pumped out like toothpaste, the die attached cracking under the stress of microscopic tug-of-war, the cooling pipes choking on chemical scale, and a slightly loose bus bar bolt turning into an electrical blowtorch due to atomic friction.
We covered a lot of ground.
We then saw how the vehicle defends itself against these invisible enemies, using a layered defense of hardwired hardware sensors and brilliant software digital twins that calculate power loss to predict heat before it even physically reaches the thermometer.
The digital twin is a marvel.
And we marveled at how it actively juggles that destructive heat to survive a sudden failure. We explored the absolute engineering paranoia of the assembly line, replacing human hands with acoustic microscopes, helium leak sniffers, and servo screwdrivers that verify electrical resistance by reading the friction curve of a turning bolt.
Truly robotic precision.
And finally, we witnessed the brutal torture tests that prove these systems can survive the most violent conditions imaginable without failing. It really highlights how modern automotive engineering merges thermodynamics, quantum material science, and high-speed computing to keep you, the driver, completely safe on the road.
It is a phenomenal synthesis of disciplines. It proved that safety isn't an accident. It is deeply intentionally engineered into every single atom of the vehicle.
But before we wrap up this deep dive, I want to leave you, our listener, with a final provocative thought. It's an idea pulled right from the very end of the source documentation we were analyzing.
Okay, let's hear it.
The spec mentions the ability to build a dynamic, fourth-order Foster RC model to simulate exactly how junction temperatures spike during different torque surges. Now, currently, this digital twin is mostly used defensively. It is used to set the safety limits and trigger the fail-safes.
Right, it's a safety net.
But I want you to think about the near future. What if our cars don't just react to heat? What if they use artificial intelligence and these incredibly advanced, mathematically perfect thermal digital twins to route power differently before the hardware even has a chance to get warm?
Oh, that's interesting.
Imagine a vehicle that knows a steep 3-mile mountain pass is coming up via GPS. It calculates the thermal load required to pull your car up that hill and preemptively adjusts its cooling pumps to maximum and actively routes electrical power through different cooler chips in the inverter to prevent the heat spike from ever occurring in the first place. The digital twin isn't just a diagnostic tool anymore. It is the future of how electric vehicles will quite literally feel their own physical limitations and proactively adapt to their environment in real time.
A fascinating prospect. We are moving from reactive survival to predictive diagnostics and ultimately to proactive environmental adaptation. The car becomes, essentially, a conscious thermal organism.
Exactly, a conscious thermal organism.
Yeah.
So next time you are cruising down the highway, the music is playing, and everything is running perfectly smoothly, take a second to appreciate that chaotic, microscopic war being waged and won thousands of times a second beneath your feet. Thank you for joining us on this deep dive into the engineering source material, and keep questioning the invisible engineering in the world around you.